Okay, good afternoon. So I was in the office hour just a moment ago. I found some of you might struggle with the matrix derivative, last two problems in the homework 0, right? So the objective of that problem is just to let you practice about how to use like matrix vectors to represent gradients or derivatives. Because in our future lectures, we'll present the models or loss functions all in terms of like vectors and matrices. And also to implement these algorithms, you'll need to derive the gradient and then call some external optimization packages such as LBFTS or contribute gradient descent. If you have taken optimization course before, you will know those algorithms. But if you call those algorithms, all the input of those algorithms are all function values and a vector, the gradient vector. So you need to be able to derive the gradient and represent in terms of matrices and vectors. So that's why we want you to do that problems. And someone asked if there are some points of references. Actually, I listed in the last slide in the lecture slides. So actually, I listed the most commonly used rules for matrix derivatives. So you can consider them as like a chain rule, matrix version of chain rule. And what you do is actually to recursively apply those matrix derivatives. Of course, you will meet some kind of tricky matrix derivatives, but don't worry, there is a link here. Matrix cookbook is kind of a Bible for matrix derivatives. So you can consider it just like dictionary. And whenever you do the matrix derivatives, you decompose your task into like derivatives over different components, and then you check the references from matrix cookbook. That's the standard procedure. Don't try to like derive everything from scratch. This is just a tool. It's just a tool. So any concerns about this? Okay, great. And let me use this. Oops. So let us get back to the course content. So I'm sorry about last lecture we ran over time because in the lecture mode, when the light is in lecture mode, it's very hard for me to see the clock in the back wall. So I ran around time. I thought it was only 4:45. Why some of you guys are preparing to leave? And, oh gosh, you're tired of me? This is the second lecture, right? And then later some guy came to the classroom and spoke to me seriously. Said, we have a class at 6. Oh, really? And I picked the phone. Wow, it's already 6. So guess what? I will watch today. So I really don't want to keep you over time. Right? So here's the plan of our today's lecture. So we'll introduce the supervised learning framework and the definition of decision tree. Since our primary focus in this class is the supervised machine learning algorithms. So we'll start to introduce the general framework about supervised learning. So what kind of key factors or key common factors you should consider whenever you want to conduct a supervised learning task. And then we'll begin to investigate various supervised learning algorithm 101, and the first supervised learning algorithm we'll study is decision tree. But today we only do some warm-up. we just introduced the concept of decision tree. What is decision tree? What does it represent? And giving you a decision tree, how can you use it for prediction? And then in the next lecture, we'll study the classical algorithm to learn the decision tree from data. And later, we'll introduce some variants of decision trees and some tricks. So let us first consider the question, what is supervised learning? As the name suggested, supervised learning should be someone teach you like hands-on, right? Hands-on teaching. Typically, if I'm a teacher, I'll give you a set of problems and also the answers, right? The correct answers, such that you can look at the problems and look at the solutions, and finally you learn how to solve the problem. Then next time, we'll give you a new problem, but in the same kind of type. You can use the similar tricks or methods you learn from existing solutions and obtain your own solution. This intuitive sense of supervised learning. But if we put supervised learning in the context of machine learning, we should be clear about two key factors. First, the instances, and second, the labels. So, following the previous example just discussed, instances correspond to the example problems, right? And labels correspond to the answers. Now, if we take a look at some particular supervised learning task, that is to automatically tag news articles, then what is the instance?
The news article itself?
Yeah, you're right. Okay. One instance is just the one particular news article. And what is the label?
Category.
Yeah, the category. The tag you're interested in. You're possibly to tag this particular news article, right? For example, sports. Of course, you can incorporate whatever tags you're interested in to serve as labels, right? For example, sports, business, politics, entertainment, right? So our task is essentially to map each specific article to a tag. Right? This is actually our goal to carry out supervised learning. Then we can consider all possible news articles. The set of all possible news articles as the instance space. And correspondingly, we take the set of all possible labels as label space. So this formed generally two factors in supervised learning. First, what is the instance space? And second, what is the label space? Right? So, in general, in arbitrary supervised learning tasks, you need to define an appropriate instance space. The instance space is a set of all examples that need to be predicted, right? Need to be classified, need to be tagged, or need to be estimated. So this is called instance space. And then we have a label space. The label space is simply the set of all possible labels. Any question at this point?
So for instance space, named does it saying like those different categories are all in one single instance space, or is it the list of like documents? Like, does that make sense?
I kind of capture a point. So Actually, instance space just consists of everything you might want to classify, or you might want to predict, but does not contain the labels itself. For example, if your task is to do the document classification, right? So what are the instance space?
The what class?
If your task is to classify the documents, the tax documents,
yeah,
what's the instance space?
All the different documents.
Yeah, all the documents.
Okay, cool. Got it.
Yeah, all the documents. If your task is to predict whether an image contains a cat, right? Then what is the instance space? All the images, no matter whether this image really contains a tag or not, a cat or not, right? It's just the instance. And what's the label space?
Cat, not cat?
Yeah, it's just two elements represent a binary prediction result. Right? Either it has cat or it does not has cat. Another example, like if our task is to predict whether the email is a spam email or not, then what's the instance space? Yeah, all the possible emails, right? No matter whether they're really important emails or just spams, they're just in the instance space. But the label space is just binary, right? Spam or not spam.
Is it still a label space if y is continuous?
Yeah, that's a good question. We'll discuss it later.
Okay.
Yeah. And then, given the instance space and label space, our task is essentially to find a mapping between each particular instance and a label, right? So if you want to predict something or you want to label something, you actually want to find an underlying function of the instance. And output of this function is some label. So when you carry out supervised learning, you always assume there is an underlying target function which maps the instance to the labels. Then our goal is to find out this target function or find out a good approximation of this target function. So actually in most cases, this target function is not only unknown, but also very complicated. You're even not sure about whether it can be expressed by some analytical forms. So at most, we want to find some very good approximations. That's it. So yeah, the goal of learning is to find out this target function, a good approximation. So from this perspective, learning is also a searching procedure. It's a search over the function space. You can imagine, or you can assume, your target function belongs to some particular family of functions, right? And their learning algorithm is trying to identify one best function. Everyone is good? Mm-hmm.
Is there also going to be a function space?
Yeah, you're right.
Okay.
There is also be a function space, which actually, in machine learning jargon, it is called a hypothesis space. But the same meaning. So actually, whatever machine learning algorithm, it actually assumes a function space or hypothesis space. We'll summarize this point later there. Then what is the protocol to conduct supervised learning? The protocol is as follows. We first collect a set of labeled data. We call it training data. So each data point is a pair of the instance and its corresponding label. Because we assume the label is actually a function of the instance. So we can consider it as a pair of function input and function output, right? And then, given this labeled training data, we develop a learning algorithm. And the input of this learning algorithm is this training data set. And the output of this learning algorithm is a learning function. So this function actually has the same input domain and output domain as the target function. So meaning that the learning function also takes the instance space as the input domain and output space or the label space as the output domain. And we hope that our learning function G is close enough to the target function Y. Ideally, we hope this learning function G coincides with the target function, but in most cases that won't be possible. So this is the whole protocol for supervised learning. So now comes a question. Can you think of other protocols?
What do you mean by protocol? Just this overall thing, or?
Just like how you learn a function, how you prepare data, how you do this kind of things. Of course, you can, right now you can assume, okay, given a fixed instance space and label space, and we have the assumption that, we have the same assumption that there is a underlying function, target function, which maps the instance space to the label space. And as we just discussed, supervised learning is to prepare a set of label training data and develop a learning algorithm. The input is the label training data, output is a learning function, right? This is the protocol. Do you have any other protocols?
Unsupervised learning?
Yeah, so what is...
unlabeled training data and classified it.
Okay. Any other suggestion?
Perhaps when you know when to stop taking data, like you could have an infinite amount of data, you probably want to stop at a certain point.
Yeah, that's another suggestion. Another idea?
Testing data to evaluate how good of a function G is.
Well, that actually is in the test part. We're trying to brainstorm other learning protocols. Any other idea?
You can just try to like derive the functions mathematically somehow.
Wow, that's cool. Although it's quite difficult.
Yeah.
That's another, of course, this is another way, but if you can derive that function, we don't need some learning procedure. It's kind of more like a human learning procedure. Yeah, all your answers are great. So actually, how do you define the learning protocol, or how do you conduct the learning protocol actually correspond to different learning framework? For example, the unsupervised learning, as you just mentioned, right? What if I do not offer you the labels of the instances? I just give you a set of instances from the instance space. I do not give you any label. Can you also design a learning algorithm that uses this unlabeled training data as input and output the learning function?
Wouldn't that be just k-means or something like that? Would that be considered a learning algorithm using k-means?
Yeah, you're right. K-means you specify k, after you specify the label space.
I mean, on all of them, don't you have to define some sort of loss function? You try to minimize, or another function you try to maximize that's your learning function, essentially?
Yeah, of course. Even if you use unlabeled training data, if you want to conduct the training procedure, most time you still need to work out a loss function or objective function. But here we just give a very, high level. We do not drill down the details about how to come out an objective function. That's something we'll discuss later. But briefly speaking, yeah. What you mentioned is right. K-means is a typical unsupervised learning. because I don't know the labels for each instance, right? But when you do the k-means clustering, actually each cluster corresponds to one label. So this is a unsupervised learning. And a third variant would be, what if I provide you a data set mixed with labeled trained data and unlabeled data? This is called semi-supervised learning. It's actually still an active topic in machine learning research. That's partly because in most of the cases, if you want to find out labels for instances, it's very costly in both time and money. But you can easily collect a large amount of examples without any labels. The question would be, how do you smartly use the information from unlabeled data to facilitate your training or your learning procedure? So that's called semi-supervised learning. And one student mentioned that what if I do some learning until some point we stop? Right? This actually relates to another view of categorizing the learning procedures. For example, what if I first give you a set of training examples and then ask you to do the test? If you perform that at some point, I offer you another set of training examples. So this is called active learning. And also, for example, if I train a robot, right? I just give you a few training data and then you just do whatever. And when you hit the wall, you get feedback from the environment. And then you adjust your environment, you adjust your strategy. And then you do it again. And whenever you feel or you hit something, you adjust the strategy, you collect data. So actually, this procedure is called reinforcement learning. You automatically get feedback from the environment and use these feedbacks to reinforce your models, your algorithm. It's called reinforcement learning. But this is another view to look at the machine learning algorithms. So actually, machine learning, the hierarchy of machine learning knowledge can be organized in different ways. Here we only view them in a static way, not in a very dynamic view, because it's very easier to understand. So let us get back to the supervised learning. The key point is that we must have a set of labeled training data. Every example must be labeled. Any questions so far?
So how do you choose your instance space? If there's like 1 trillion images on the internet, how do you choose which ones to use? Is there just like
although in theory it's it could be difficult, but in practice it's not that difficult. You just have some kind of concept. You choose an instance space, but it does not necessarily mean you will use all the instances in this instance space for training. In most cases, or 99% of cases, you just collect a subset of instances, all of the instance space for training. But you should be clear, abstractly, what is your instance space?
What if you had, for the training data, you had instances paired with a label that it's not, or like a set of labels that it's not?
That's not true. You mean wrong labels or?
Yeah, and you tell the learning algorithm these are non-examples. Is that a model that's used?
Yeah, that's a very good question. It actually relates to a very important concept called overfitting. And although when we learn those algorithms, we usually assume, okay, the training data is clear and correct, nothing wrong with them. But actually, when you perform machine learning in practice, you should give up this assumption. You should always assume the data is kind of noisy. There could be some mistakes in both the instances, the representation of instances, also the labels. And then, to avoid or to minimize the loss made by the noisy data, you have to conduct several post-processing procedures. For example, you need to do cross-validation to choose appropriate hyperparameters you need to do the post-pruning of the decision trees to avoid growing too large, too depth, such that it can fit the noises so well. If it fits noises so well, then when we are giving new examples, it could perform very badly. Right? But we'll talk about this later. Any other questions? Okay, great. So now, suppose we have finished the training procedure by using our supervised learning protocol, and we have obtained a learn function, which we denoted by gx. Right? The next question would be, how can we make sure that our gx is close to the target function fx? How can we do that? First, you should keep in mind that we don't know the exact form of fx. An idea?
You define an error based on training data come in and map it over to some data that isn't part of your training set, and then compare, actually have a user go through and say, yes, this is right, this is wrong, eventually you get it.
So you mean, okay, I can just use my learn function to make a prediction on the training data and compare our prediction on training data with the true labels and say whether we're correct or not, right? Okay, that sounds reasonable. But is there any problem?
So if we're just using the training data to evaluate something like, we could just get really good at the specific instances we have and what we're training on, essentially overfitting or whatever. That's a potential problem with this method.
Yeah, and your opinion?
I was going to say what you said.
Yeah, okay. Yeah, that's good. All your points are good. So basically, you're right. We should collect some examples for testing. But using training examples for testing is problematic. Why? Because we want to compare the real generalization performance of a learned function, right? You must make sure the fairness. You must ensure the fairness. So if you use training data to evaluate your prediction performance, I can come out very stupid learner. I just memorize all the training data, right? So whenever I test, giving you example, now that it is in my memory, I just retrieve it. I store it in some database, right? Retrieve it and report. I got 100% accuracy, but actually I do nothing. So basically, the strategy is right, right? Now that we don't have some analytical form, we don't have some analytical form of target function, right? To examine whether our learned function g is close enough to the target function, we need to sample some test examples, right? And then compare the true label and prediction from our learned function. If they are close, okay, we're good, right? But the key problem is that we cannot use the training examples for test. It's just like cheating. It's just like cheating. I cannot give you the answer and let you answer the problem. Right? So this is a very important rule. Right? Basically, our testing procedure is like this. We draw test examples randomly from the instance space because in many cases, instance space contains is infinitely large. It contains numerous examples. You cannot invert all of them, but we can randomly draw them and then draw test examples and compare the true label and our target function's output. And if they are close or they are the same, we're good. Is it enough to use just one test example?
No.
Why?
You don't really know how good it is in general. I know for one instance.
Right, right. So actually, you should draw a lot of test examples. The more, the better. And the more test examples you use, the more accurate your generalization performance estimation will be. Right? This actually can be proved based upon classical statistics theory, like large numbers law. The average is approaching closer and closer to the true value when you increase the number of samples. And the basic rule, keep it in mind, never ever incorporate test example during training. So in the future, if your boss asks you to develop some machine learning algorithms to make some prediction, if it turns out your model works perfectly well and much better than all the existing methods, don't celebrate too early. Check whether you happen to put test examples into training examples. It's very important. And
Sorry, could you explain the test example again? Does that include instance space and label space, or is that just including instance?
Test examples.
Yeah, the test example.
Of course, it involves both the instance space and label space, right? If we want to test, we need to know the answer, right? So we must have the label for the test instance.
And then f of x versus g of x, is g of x the function learned from the test example, and f of x?
No. The function g is learned from the training examples.
From the training. And
Yeah.
f of x is what?
fx is actually the true label for the test example. For instance, if I can collect a set of, if your task is to predict your emails or spam emails or not, right? You just collect a bunch of emails, and you know whether they're tagged or not, right? That's the true label. And suppose you run your neural networks, and you generate some prediction that corresponds to GX, right? You just compare your prediction from your neural network and the true labels. And if they're consistent, it means that you're well done, right? Your algorithm is good. If they are very different, then it's problematic. Any question at this point?
Does a test example add a new instance to the instance space?
No. Instance space is fixed there.
It's fixed, and then they're just...
They're just a subset of instances sampled from instance space. Of course, training set, the training instances are also sampled from instance space, but you must be sure they are not overlapping. So this is a very important principle. So it is a very common mistakes made by machine learning practitioners. Very, very common, even for highly experienced person. So whenever you find your algorithm performs so well, just check the first whether you happen to put the test examples into the training set. Yeah. So here, let us summarize the general setting for supervised learning. So basically, to conduct supervised learning, we should first collect a set of training examples in the pairs of instance and labels. Of course, here we assume the labels are a function of the instance, so we denote them by fx. Right? And then the input x, that is the instance, in a computer program is usually represented by vectors, a vector of numbers. We call those vectors as features. The reason is that computer programs can only deal with digits, right? You cannot throw a piece of newspaper in front of computer programs and tell it, classify this, tell me whether this is a business report or not, right? You need first to digitalize it. So the procedure to digitalizing those raw instances is called feature extraction. That is, you need first to turn or convert the raw instance into a vector of numbers. We call this a vector of numbers as feature vector. For example, your feature vector could be a binary vector. Or your feature vector could be continuous vector, meaning that every feature value is continuous. To give you a concrete idea, for example, my task is to predict whether I am handsome or not. And what kind of features can you extract to represent me? An idea?
height.
Yeah, age, height.
Facial features.
Yeah, you can construct a lot of features, right? Age, height, and whether I'm going to be bald, or whether my dressing taste is good, or and etc. Right? You can create a lot of features, and then you concatenate all these features into a vector. This is my representation, and then in the supervised learning algorithm, everything which I deal with is those feature vectors. And we won't cover too much about how to extract those features, but I can tell you in practice, extracting features are really important. And also depends on applications and domain knowledge. So experienced machine learning practitioner will always extract useful features. And I can tell you, as long as you identify the useful features, you'll have an 80% chance to succeed. No matter what kind of machine learning algorithm you use, your performance won't be bad. And then the goal of supervised learning is to find a good approximation of the underlying target function f. And then here we go. We talk about how the label space determines the types of tasks. So actually, different label space defines different types of tasks. If our label space is binary, like just contain 2 elements, this task is called binary classification, because your label is just either -1 or 1, either 0 or 1. Right? It's called binary classification. If a label space is discrete, like 1, 2, 3 until k, right? Then your task is called multi-class classification. Someone just asked if it is possible that you have a continuous label space. The answer is yes, of course. If your label space is continuous, filled with like real numbers, your task is called regression. And in that case, actually your label space is infinite. Okay, any questions so far? It's just a summary of the general supervised learning setting. Okay, good. So whenever you conduct a supervised learning, here are a few questions you need to decide, implicitly or explicitly. So first, as we just mentioned, what is your instance space? That determines what kind of data you can collect, what kind of data you're gonna proceed, and what kind of examples you want to predict. And then, what is our label space? Is a label space just contain 2 elements? Then we're doing binary classification. For example, you want to predict your email is spam or not. This is binary classification, right? Because the label space only contains 2 elements. If you want to predict the stock prices, then the label space is continuous, right? Full of real numbers. And the third question would be, what is our hypothetical space? As someone just mentioned, what is the function space? What is the family that could potentially contain the target function? So actually, any specific machine learning algorithm will assume a hypothetical space, a function space. And the learning procedure is essentially to use the training data to guide our search over the hypothetical space. Learning is a searching procedure. And we'll end up with a good approximation, either a good approximation to the target function in your hypothetical space, or some real target function, if it is possible. And then what is your learning algorithm? This is pretty intuitive, right? You conduct supervised learning. You should choose what particular algorithm you want, like decision trees, support vector machines, Gaussian processes, neural nets, logistic regression, and so on. Right? And most machine learning users only know what kind of learning algorithm they're going to use. But actually, they do not necessarily need to know what's the mechanism of those learning algorithms. It's our task in this class to understand why we like to use those learning algorithms, what's the benefit, what's the disadvantages. And finally, what's the evaluation metric? Given you the learn function, how can you evaluate the performance of your learn function? For continuous labels, how do you evaluate? For a binary classification or multi-classification, how do you evaluate? An idea?
Just how often it's within a certain range of getting the answer right, a number that classifies the image correctly.
Yeah, that's one solution. That's I guess that's mainly for like a classification case, right? So what if our label space is continuous? We're doing regression.
Used to like some kind of sum squared error or something like that that measures a distance from the predicted to the actual output.
Yeah, you're right. Because continuous value, we cannot say, it's very hard to say, okay, the two values is exactly the same, right? But we can calculate the difference between them. Right? The smaller the difference, the better the approximation or the prediction. So actually different tasks correspond to different evaluation metric. And different evaluation metric also leads to different loss functions or objective function. Okay, these are the supervised learning. And based on how we conduct the learning protocols, as we just mentioned, here I give a rough taxonomy of machine learning models. And here is our primary focus this semester. And unsupervised learning, according to our plan, if we have some time, we'll introduce the classical clustering algorithm, dimensional reduction, etc. And for semi-supervised learning, it sounds very cool, but most semi-supervised learning algorithm is to combine loss functions from supervised learning and unsupervised learning. So you can extend almost all those supervised learning algorithms here to their semi-supervised version. So we won't spend too much time. I won't spend time on semi-supervised learning. When you know what is supervised learning, it's very easy to extend to semi-supervised learning. And among those supervised learning algorithms, we'll start with decision trees. That's our first machine learning algorithm, and first our first entry. So we'll introduce first what is decision tree? The representation. So we see decision tree is essentially a compact data representation or compact data summary. And then we'll introduce the classical decision tree learning algorithm called ID3 algorithm, invented about 30 years ago, but still very widely used, very useful. And ID3 algorithm essentially use a greedy heuristics based on the so-called metric information gain to create and span trees until certain conditions are satisfied. And this algorithm is very important. Everybody must be able to implement this algorithm. And then, based on ID3, we will introduce its variants and extensions. For example, when the tree grows too large, too wide, or too deep, how can we post-prone it? And why should we prone decision trees? One usage is, as you just mentioned, we need to avoid being affected by those noises in data. And also we can introduce other metrics or heuristics like Gini index to create decision trees. Any questions so far? Okay, why would we study decision tree? I think I briefly mentioned in our very first lecture and introducing what kind of topics we would like to cover in our whole semester. Right here, I want to emphasize again. So at least there are 3 reasons. First, decision tree is very simple and intuitive. You will see, decision tree are essentially a set of rules. So there's nothing more intuitive than using rules to perform prediction and decisions, right? It's very similar to our human beings' thinking and decision procedure. So it's very easy. And then the very important, important property of decision tree is that it has excellent interpretability. So interpretation is very important for machine learning. Decision tree has excellent interpretability, again, because of the rules. The learning, training, and prediction of decision trees are totally transparent. So when you use decision tree to make prediction, you know why it works. You know why it fails. And they can debug, okay, it's because of some node it fails, and then I just supplement this node with more training data. That's it. It's unlike right now, there are a lot of hypes about the deep neural nets, right? The deep neural nets has a big problem in interpretability. Whenever you make a mistake, you actually don't know why. What you see is just hundreds of layers, and so many nodes, and very highly nonlinear activation functions. And why it generates a bad case, I don't know. So that's the key answer why decision trees are still widely used after being invented for like 30 years or 40 years. And someone may argue that decision trees are still weak, right? Many tasks. But I can tell you, by using ensembling or integration procedure, decision tree can be promoted to be very strong and can be state of the art. So for example, the gradient boosting tree, I can give you a gossip. And many researchers in the online advertising areas try to build out deep neural nets to predict the rate prediction. This is a very important metric in online advertising. And I read a lot of papers from the top machine learning conferences or data science conferences. And many people claim that, wow, my deep neural nets work so well, beat all the traditional methods. But then I got changed when I met a senior professionalist in the industry. He told me that the engineering industry have never ever proved that machine learning, deep learning can really beat gradient boosting trees. So gradient boosting trees is just the enhanced version of decision trees. So don't look down upon decision trees. It's very useful. So today we'll only do some warm-up. We just want to know what are decision trees. So before we look at some concrete examples, I just summarize the definition of decision tree to give you a general sense first, and then we'll look into the detailed tree. Right? So first, decision tree, as the name suggests, it is a hierarchical structure that represents the data with a divide and conquer strategy. And in this tree, each node represents a data subset. The root node represents the whole data set. And then each leaf node or each internal node represents a subset of data. So the creating of decision tree is essentially to partition the data recursively. In the meantime, each node is associated with a test feature. The test feature is used to help us to partition the data. How do we partition the data? For each feature value on the node, we just create a branch. The branch is created for every particular value that feature can take. So every data samples in the current subset data whose feature value take that specific value will be formed into a new subset. Just imagine, it's just like a partition according to specific feature values until the leaf nodes. The leaf nodes represent some points we stop the partition procedure, and the leaf nodes give you the labels. That's the general description of decision trees. So I guess you are not very satisfied with this very looks like kind of a weak description, right? And the general idea for decision tree learning is to construct decision tree to represent the training data. That's the key idea. So now let us look at some concrete example, and then get back to this general description. You will know what is decision tree. So suppose our task is to classify the shapes. Here's our training data, and each shape is classified into 3 possible labels: A or B or C, right? So first, to create a decision tree, we need to collect all its possible features or attributes. So what kind of attributes do we have? Yeah, 2 attributes, right? Shape and color. So before we do this, can we consider how to predict a right triangle? Feels a little difficult, right? It's not very intuitive to give you a right triangle, to predict the right triangle. Anyone give a guess? B. Why?
You've been doing with triangle.
It's triangles and red.
Is the triangle right? What's the meaning? I guess you want to say all the triangles are labeled as B, right? So red triangles should also be labeled as B. All the training examples are only blue triangles, right? You're right. And actually the learned decision tree or the created decision tree will reflect this point. Yeah. So it's color and shape. So now let us try to create a decision tree, right? Suppose we start with color. That is our rule node, which represents all the training data, all the data set, right? And we associate the rule node with the test feature, which is color. How many colors do we have? 3 colors, right? Red, blue, blue, green, and red. Right? So we create 3 branches. Blue, red, green. And then for all the examples which has the same color, we put them in one subset, which correspond to 3 new nodes, right? So let us first look at the red shapes. We can see all the red shapes are labeled as B, right? That means the samples here, the subset of shapes that the samples here, they have pure labels. They have unique labels. So we don't need to split them anymore, right? We just stop here and report the label is B for this subset. And then let us look at another 2 attribute values, blue and green, right? So first let us look at blue. So, I'm sorry. So for blue, actually we have a mixed labels, right? We have 2 blue circles, 2 blue triangles, and 1 blue rectangles, right? So here we associate the node with another attribute, it is shape. Because we have 3 types of shapes, triangle, square, and circle. So we can partition the remaining data set, I mean the blue shapes, according to their detailed shapes into 3 parts. Right? So now, for blue triangles, what's the label? Here, right? So remember, this node actually represents all blue shapes. It's a subset whose color are blue, right? So it contains 2 blue circles, 2 blue triangles, 1 blue rectangles, right? And now we further partition this data subset according to the shape. And now we partition them according to triangle shape, meaning that we have blue triangles, which are here, right? And now the labels for blue triangles are all B. So we stop. We enter leaf node, reporting the label to BP. And similarly, among the subset of shapes here, what are the squares? We'll have only one blue squares, right? And also, of course, they will only have one label, so the label is A. And similarly, blue circles, we have two blue circles. Both are labeled as C, so we'll enter a pure label. Then we'll create a leaf node with C. Okay. Any question at this point? Very easy, right? Very intuitive. And similarly, for third branch, means green shapes, right? We can do the same thing. For green shapes, we have two green rectangles and two green circles. Right? So we need to create a node again and split them according to the detailed shapes. Right? For square shapes, we have two green shapes, two green squares, which are both labeled B, so we create a leaf node with the label B. And for green circles, we have two green circles, so we create a leaf node because they have the unique label. So now we finished the decision tree.
I'm a little confused why you're labeling those as labels as opposed to instances.
Yeah, because all the instances are
Like
here.
at the top, sorry, no, at the top, you say like label C, label C, label B, label A. I would think that you would put those as instances instead of labels.
No, it just means, okay, all those instances here are labeled B. So their labels are B. The instances are those like triangles and the circles with different colors. And here is just, okay, this blue circle is labeled as A, this blue circle is labeled as A, and this green rectangle is labeled as B, etc. Any question?
Yeah, how do you choose the order of color and shape?
Very good question. I just randomly choose them. I choose it by tossing a coin.
But like in a different example, would it matter?
Of course it matters. Yeah, that's the question. That might be a homework solution, homework question for you. But,
What if you had a repeat, like a blue circle and C and an A?
blue circle and C and A?
Yeah, like what if it was a repeat?
Was what?
What if it was a repeat? Like it goes color to shape, circle, and say if it wasn't C and an A, then what would you do?
You mean you switch the order to create the tree? You will use the shape first and then do the color?
If they were mislabeled.
Mislabel.
Or like
Yeah.
Or there are two labels for one.
Oh no, this we don't allow two labels for one.
Okay.
Yeah. That's not our setting in supervised learning. In supervised learning, we always assume one example has one instance has one particular label. If I have multiple labels, it must belong to different meaning.
So this was our training data right here, right? That's
Yeah.
what we built the tree out of. So what if when we were testing it, the testing data handed us a green triangle?
Very good question. That means the decision tree right now we're creating still has some deficiency. It actually does not cover all the test examples. So that leads to the question. So first, let us solve the problem one by one, right? So first, let us say how to use this decision tree for prediction, right? And back to our question, like how can we predict a right triangle? We just mentioned, right? Before we talk about creating a decision tree, how can we build up a right triangle? How do we do that? We just start with root, right? and recursively test each feature and going to the corresponding branches and end up with some label, with leaves to report the label. So for green, for the red triangle, we first test the color, which is red, and then enter this node. And we stop here because it's a leaf and it reports B. That's it. So it's consistent with our intuition. So now we come to your problem. So what if we want to test the label for green triangle? We test the color, which is green, and then we stop here. We stop here, right? There's no branch showing that there's a triangle. How can we do that? Of course, this decision tree is not complete. It's not sufficient. But here I want to ask you, given this decision tree and you're stuck here, can you provide any solution to give a label for that?
Do you report one at random or see which one's most similar to the triangle? So the square maybe, since it has 4 corners rather than 3.
Yeah, that's one strategy. So
If you had built your tree backwards, like if you had done shape and color, you'd get an answer with B.
Probably. You can try. Yeah. That's an exercise, actually. Later we'll see this exercise. Of course, when you switch the order of the attributes to create decision tree, you might cover the case, right? But essentially, when we learn the ID3 algorithm, it guarantees that we won't meet such kind of corner case. It ensures that every test examples will finally end up with some leaf node. But here, for this particular case, the reason we don't have a triangle branch here is because the subset of shapes associated with this node does not contain any triangles. The lack of all the subset which has triangle shapes is actually empty, right? So in this case, we usually use the majority label in this subset as a label. That's one strategy. Of course, you can invent other strategy, like we can step back forward and go to here. That represents the whole data set. Then we take a look at the most common labels. So actually, decision tree is what? Is a set of rules, right? So when you do the prediction, you're actually following a rule. From root testing feature, if the feature test passes along some branch, you go to another feature and test the feature, and go through another branch and finally end up with a label. So each path actually represents a particular rule. And all the paths follows a set of rules. It actually form a conjunction of rules. That's regard to the expressivity of decision tree. Actual decision tree is expressive enough to represent all kind of Bloom functions. So what is Bloom functions? Bloom function means that all the input variables are Bloom and output is Bloom. And it's not hard to show that decision tree can represent all types of Bloom functions. So this is an equivalent representation of decision tree. Right? You write down one path, convert it into a logic rule, right? So color is blue, shape is a triangle, and label is B, right? And then you combine with another path, which turns out to be another rule. So actually, you can succinctly represent decision tree in conjunction rules. So generally, outputs of decision trees are discrete categories, but it can also do the regression. So how can we do that? An idea?
Ranges?
Ranges.
If it falls within a certain length or range.
But you usually report a specific real values for regression, right?
I mean, you could report that, but yeah, I don't know.
The same thing, right? You can do the average. like when you stop the leaf nodes, of course, there is no some pure labels because all the real numbers, right? Then at this time, you just take the average of the remaining all responses or outputs of the examples and report the average. That's called regression tree. The key point is that when do you stop expanding the tree and then enter the leaf node, which we'll discuss later. And also decision tree are methods for handling noisy data. And as we will say, later noisy labels or features can also be handled by decision trees smoothly. And we'll talk about pruning trees with noise, etc. And another issue is that the instance we have seen, the decision tree instance we have seen, all use categorical features, right? So we will create a branch is that correspond to some balloon text, right? But what if we have attributes to be numerical? For example, the height or the weight. In this case, how can we create new branches of decision tree? An idea?
Would you like a cutoff value that like breaks it into ranges?
Yeah. Good point. Any other solution? So the basic idea is to discretize. So we have two methods to do the discretization. First, we can create many bins, right? And each feature value, each specific value falling in some bin will be turned to another binary feature. So we can create the branch, right? Or we can use some threshold. As you mentioned, it's actually cutoff, right? So if it is less than threshold, we create a branch. If it is bigger than threshold, we create a branch.
So could you describe the discretizing again?
Like for example, if I have a continuous feature, I can partition them into 3 bins, right? Negative infinity to 10, to minus 10, minus 10 to 10, and bigger than 10. I have 3 bins. So every time when I test the feature, I just test in which bin the feature value falls in, right? And for it falls in a specific bin, I create a specific branch. Give you a detailed example here. Right? Suppose I have 2 numerical features, x and y. And here I create 3 bins for each of them. Less than 3, between 1 and 3, bigger than 3 for x. Less than 5, between 5 and 7, and bigger than 7 for y. And then we can use this to create a decision tree like this. So you can see the test feature here. X less than 3, create the left branch. X bigger than 3, create the right branch. And etc. This is a commonly used strategy to deal with the numerical features. And one thing I want you to be aware that although decision tree is simple and easy, it does not mean it is a linear model. Why? From this example, we can say if we draw the boundary between the positive examples and negative examples, the boundary is not a line. The boundary is nonlinear. So even this simple decision tree with set of rules, it can correspond to nonlinear classifier. So I never claim that decision tree is simple linear models. So summary, decision tree. First, it is a compact data representation, as we have mentioned, right? Starting from node and recursively partition the data according to the test features associated with each node, right? And it's also a natural representation. Think of 20 questions, right? You can partition the data according to the answer of 20 questions. Very similar to human thinking and decision procedure. And predicting with the decision tree is easy because we can start with a node and pick up each test features and go along with the branch and go down until we reach a leaf node. And clearly, given data set, there are many decision trees that can represent. I guess I I plan to ask you, a question, but some of you have mentioned this problem very early, right? So I guess I won't need to repeat. Of course, if you change the order of the attributes to create a tree, very probably you'll end up with a completely different tree. So give you an exercise, the same set of shapes. Try to use shape to partition the data set and use color. Say what kind of symmetry can you get? All right, we stop here today.
How big does he want the course to be? On the board, yeah. I'm a math major, so.
Yeah, you just, you're from math?
Yeah.
I think you can write them in
The whole homework? Yeah.
one and a half.
Okay, for like the very first problem, it says proof, but it's like, when we did, I don't know if you have an equivalent, but like real analysis, they started off very basic like that, so I don't know how much, Okay.
It's like you do
Yeah. Okay, cool. Thank you.